Picture this: a world so close to the Sun that its surface bakes at temperatures hot enough to melt lead, where the landscape should be frozen in time, unchanging for billions of years. Yet, when astronomers peer at Mercury through their telescopes, something extraordinary defies all expectations. 26 craters, scattered across its scorched terrain, appear to have shifted position over centuries, creeping across the planet's surface like ghostly shadows. This isn't a trick of the light or an optical illusion. It's a real, documented phenomenon that's left scientists scratching their heads. How can craters, those ancient scars from cosmic collisions, move on a planet with no tectonic plates, no active volcanoes, no obvious force to push them? Mercury has always been a world of extremes: the smallest planet, the fastest orbit, the most dramatic temperature swings. But this discovery adds a new layer to its mysteries, one that challenges everything we thought we knew about how planets evolve. Think about it: craters are supposed to be the ultimate time capsules, preserving the moment a meteor struck, frozen in place for eons. So when they start to wander, it's like finding footprints where none should exist. Some researchers suggest gravitational tugs from the Sun might be at play, warping Mercury's crust over time. Others propose that the planet's enormous iron core, cooling and contracting, could be causing the ground to shift in unexpected ways. But the truth, we're still piecing it together, and that's what makes this story so thrilling. This isn't just about Mercury, it's about rewriting the rules of planetary science. If craters can move here, what does that mean for other worlds? Could similar phenomena be hiding in plain sight across the solar system, waiting to be discovered? Today, we're going to unravel this cosmic detective story, tracing the clues that led astronomers to these wandering craters, examining the wildest theories, and exploring what this means for our understanding of how planets, even seemingly dead ones, stay alive with hidden activity. By the time we're done, you'll never look at Mercury or any crater in the night sky the same way again. So buckle up, we're diving deep into one of the solar system's most puzzling enigmas. The mystery of Mercury's wandering craters began to unfold when NASA, a messenger spacecraft, the first mission to orbit the tiny planet, started beaming back images of its scorched surface in stunning detail. For 4 years, from 2011 to 2015, Messenger mapped every crater, cliff, and plain, creating the most comprehensive portrait of Mercury ever seen. But when scientists compared these fresh images with older observations, some dating back to the 1970s from NASA, a Mariner 10 mission, they stumbled upon something impossible. 26 craters weren't where they were supposed to be. The shifts were small but undeniable, like landmarks on a map that had quietly crept a few hundred meters over the centuries. At first, researchers wondered if it was an error, a glitch in the data, or a miscalibration between different spacecraft instruments, but the evidence held up. These weren't blurry, uncertain measurements. These were precise, repeatable discrepancies, craters that should have been static, frozen in time since the solar system's violent early days had moved. The implications were staggering. If Mercury's surface could shift like this, it meant the planet wasn't the geologically dead world we'd assumed. Something was actively reshaping it, something no one had accounted for. The scientific community scrambled for explanations. Some proposed that Mercury's extreme temperature swings sweltering under the sun's glare by day, plunging to freezing cold by night, might be causing the ground to expand and contract over time, subtly warping the landscape. Others pointed to the planet's massive iron core, which makes up nearly 85% of its radius, As that core cools, it could be causing the entire planet to shrink, wrinkling the crust like a drying apple and shuffling surface features in the process. But the most tantalizing theory, Mercury might still harbor traces of tectonic activity hidden beneath its battered exterior. This discovery didn't just rewrite Mercury's story, it challenged our understanding of how rocky planets behave over time. If craters could wander here, where else might it happen? Suddenly, worlds we'd written off as static museum pieces seemed full of hidden potential, their surfaces whispering secrets of unseen forces at work. And it all started with a handful of images and a question no one expected to ask. Since when do craters have legs? Mercury's geology reads like a list of contradictions. A planet that shouldn't move, yet does. A surface that appears dead, yet crackles with hidden activity. Unlike Earth, where continents drift on tectonic plates, Mercury's crust is a single, unbroken shell, rigid and unchanging for billions of years, or so we thought. The discovery of shifting craters shattered that assumption, forcing scientists to reconsider what's really happening beneath its sun-scorched surface. One leading theory points to Mercury's brutal temperature extremes. During the day, surface temperatures soar to 430 degrees Celsius, hot enough to melt zinc, while nighttime plunges to minus 180 degrees, colder than Antarctica's deepest freeze. This 800-degree swing isn't just a climate quirk, it's a planetary scale stress test. Rocks expand when heated and contract when cooled, and over millennia, this relentless thermal cycling could subtly warp the landscape. Imagine bending a paperclip back and forth until it weakens and snaps. Now picture that happening to an entire planet's crust, grain by grain, century by century. Over time, even small shifts could add up, nudging craters out of place like furniture sliding across a warped floor. But here's the catch: thermal expansion alone might not explain the full story. Some craters appear to have moved farther or in different directions than this process should allow, hinting at deeper forces at play. That's where Mercury's colossal iron core enters the picture. Proportionally, it's the largest core of any rocky planet in the solar system, a molten behemoth that's slowly cooling and solidifying. As it shrinks, the entire planet contracts, crumpling the crust like a deflating balloon. NASA's Messenger mission documented thousands of lobate scarps, cliff-like wrinkles scarring Mercury's surface, evidence of this global squeeze. Could these tectonic wrinkles be redistributing stress across the crust, causing certain regions to shift more than others? It's a compelling idea, but there's a twist. Some wandering craters aren't near these scarps at all, leaving gaps in the explanation. Then there's the wild card: gravitational nudges from the Sun. Mercury orbits so close to our star that the Sun's gravity exerts an extraordinary pull, warping space-time itself around the planet. Over centuries, this relentless tug might distort Mercury's shape ever so slightly, creating tidal forces that could theoretically rearrange surface features. It's a fringe hypothesis, but in a mystery this baffling, even the improbable deserves a second look. What makes this puzzle so electrifying is how it forces us to rethink the very definition of a dead world. If Mercury, with no atmosphere, no water, and no plate tectonics, can still reshape itself, what other surprises might lurk on seemingly static planets? The answer could rewrite textbooks, proving that even in the quietest corners of the cosmos, change is the only constant. Among the most compelling explanations for Mercury's wandering craters is the hidden role of volatile substances like water ice that transform from solid to gas with surprising ease. Deep beneath Mercury's blistering surface, pockets of these frozen compounds may lurk, remnants of ancient comet impacts or trapped during the planet's chaotic formation. When sunlight finally reaches them, either through cracks in the crust or shifts in Mercury's tilt, these volatiles don't just melt, they vanish, sublimating directly into gas with explosive force. The result, the ground above them loses its support, collapsing like a trapdoor or sliding sideways as if pulled by invisible strings. This theory gains traction when you look at the map of displaced craters. Many cluster near Mercury's poles, where NASA messenger probe confirmed the presence of water ice hiding in permanently shadowed craters, places so cold and dark that volatiles survive for billions of years. But over centuries, even these frozen vaults might not stay sealed. Mercury's axis wobbles slightly over time, a phenomenon called axial precession, which could allow faint sunlight to creep into previously sheltered areas. As the ice sublimates, the once stable terrain becomes unstable, triggering slow-motion landslides or gradual sinkholes that drag surface features with them. The process wouldn't be dramatic like an earthquake, it'd be achingly slow, a geological whisper. Picture an ice cube left on a countertop, shrinking almost imperceptibly until the glass resting on it tilts. Now imagine that ice cube is the size of a city, buried under miles of rock, and the glass is a crater 10 kilometers wide. The effect would be subtle but relentless, a quiet rearrangement of the landscape over generations. Yet skeptics point out a gap in this theory. Not all wandering craters sit near known ice deposits. Some meander across Mercury's sun-baked equator, where temperatures should have vaporized any volatiles eons ago. Could there be other, more exotic compounds at play? Sulfur, for instance, sublimates at much higher temperatures than water ice, and Mercury's crust is rich in sulfur-bearing minerals. If sunlight triggers sulfur deposits to vaporize, even in small amounts, the resulting gas could act like a lubricant, letting slabs of crust slide past one another. This volatile hypothesis does more than explain moving craters. It paints Mercury as a world of hidden dynamism, where sunlight doesn't just bake the surface but reaches into the shadows, reshaping the planet molecule by molecule. It's a reminder that even in the harshest environments, change is always stirring beneath the surface, waiting to be uncovered. The sun's grip on Mercury is unlike any other force in the solar system, a relentless, crushing embrace that shapes every aspect of this tiny world. Just as Earth's oceans rise and fall with the moon's pull, Mercury's solid surface might be bending under the sun's gravitational sway, flexing like taffy stretched over cosmic time. Imagine holding a rubber ball close to a powerful magnet. Even if the magnet doesn't visibly move the ball, its invisible force distorts the material in subtle ways. That's the kind of influence the sun exerts on Mercury, warping its crust millimeter by millimeter over centuries. Tidal forces are usually associated with liquid oceans, but on Mercury, they could be working on solid rock. As the planet whips around its orbit at breakneck speed, completing a year in just 88 Earth days, the sun's gravity creates bulges in its crust. These aren't dramatic, mountain-sized swells. They're microscopic shifts, a stretching and compressing of the surface that adds up over generations. Picture a sheet of aluminum foil left in the sun, slowly buckling as heat expands and contracts it. Now replace the foil with a planet's crust, the heat with gravity, and you've got a recipe for creeping change. The math behind this is fascinating. Mercury's orbit is highly elliptical, meaning its distance from the sun varies wildly, from 47 million kilometers at its closest to 70 million at its farthest. That difference matters because gravity weakens with distance. When Mercury is near perihelion, its closest approach, the sun's pull is twice as strong as when it's at its farthest point. This constant yo-yoing creates a rhythmic stress on the planet's crust, a push and pull that might rearrange surface features like crumbs on a shaken tablecloth. But here's where it gets even stranger. Mercury is locked in what's called a 3-to-2 spin orbit resonance, meaning it rotates 3 times for every 2 trips around the Sun. This odd dance means some parts of the planet experience the Sun's strongest gravitational tugs more frequently than others, creating uneven stress points. Over time, these imbalances could cause certain regions to deform more than others, explaining why some craters wander while others stay put. It's like rolling a lump of clay between your hands. The pressure isn't uniform, so some areas stretch while others compress. Critics argue that tidal forces alone might not account for the scale of the observed crater movements. After all, the Sun's gravitational influence, while immense, is still a gentle nudge compared to the forces that drive Earth's earthquakes or Jupiter's moonquakes. But Mercury's surface has had billions of years to accumulate these tiny nudges, and in geology, patience is power. A river doesn't carve a canyon in a day, and gravity doesn't reshape a planet in a century, but give it enough time, and the impossible becomes inevitable. What's truly mind-bending is how this challenges our Earth-centric view of planetary behavior. We're used to thinking of worlds as either geologically dead or alive, static or dynamic. Mercury defies that binary. It's a planet where change happens not in fiery eruptions or continental collisions, but in the silent, imperceptible flecks of rock under an unyielding star. If the Sun's gravity can move mountains here, what other hidden forces might be at work across the cosmos, rewriting landscapes too slowly for human eyes to see? Mercury's surface isn't just hot, it's a furnace by day and a freezer by night, with temperature swings so violent they'd shatter most materials on Earth. This 800-degree roller coaster doesn't just make Mercury inhospitable, it might be the very thing reshaping its landscape. Picture a sidewalk in summer, buckling under the heat as concrete slabs push against each other. Now imagine that same process happening on a planetary scale, where the sidewalk is a crust of rock and the summer lasts for centuries. That's the essence of the thermal expansion hypothesis, the idea that Mercury's extreme temperature swings are slowly, relentlessly warping its surface, nudging craters out of place like puzzle pieces on a warped board. The mechanics are deceptively simple. When rocks heat up, their molecules vibrate more intensely, causing the material to expand. Cool them down, and those molecules contract, tightening like a clenched fist. On Earth, this effect is minimal. Our atmosphere and oceans buffer temperature changes, and daily shifts rarely exceed a few dozen degrees, but Mercury has no such cushion. Its airless surface bakes under unfiltered sunlight, then plunges into the void of space's cold embrace, creating a daily cycle of expansion and contraction more extreme than anywhere else in the solar system. Over time, this relentless thermal cycling could fatigue the crust, creating microscopic cracks and stresses that accumulate into visible movement. Here's where it gets fascinating. Unlike Earth's crust, which is broken into tectonic plates that slide and shift, Mercury's outer shell is a single, unbroken layer, a global lid with no obvious way to release stress. Without plate boundaries to absorb the strain, the planet's surface might behave more like a giant pane of glass, rigid until enough pressure builds to make it snap or warp. Some researchers suggest this could explain the lobate scarps, those long, cliff-like wrinkles crisscrossing Mercury, as well as the wandering craters. As the crust expands and contracts, it doesn't just move up and down. It could slide laterally, carrying surface features with it in a slow, inevitable creep. But skeptics raise a crucial point. If thermal expansion were the sole culprit, why don't all craters move uniformly? Observations show that some shift dramatically while others stay anchored, as if the planet's surface were a sheet of ice with patches that inexplicably refuse to melt. One possibility lies in Mercury's composition. Its crust isn't a uniform slab, it's a patchwork of different rock types, some more brittle or heat-sensitive than others. Basalt flows from ancient volcanic eruptions might behave differently under stress than impact debris or primordial crust. A crater sitting atop a dense, heat-resistant rock layer could resist movement, while its neighbor, perched on a weaker substrate, might inch forward with each temperature cycle. There's also the question of timescale. Thermal expansion can explain small shifts over centuries, but some craters appear to have traveled farther than the math predicts. This discrepancy has led scientists to wonder whether Mercury's past holds clues to its present. The planet likely formed under vastly different conditions, perhaps with a molten surface or a thicker crust that's since eroded. If the crust was once more flexible, ancient thermal stresses could have primed certain regions to shift more easily today, like old scars that reopen under pressure. What makes this hypothesis so compelling is its universality. We see similar processes elsewhere in the solar system, just on smaller scales. The moon's surface expands and contracts with temperature changes, causing tiny moonquakes. Mars boulders fracture under thermal stress, creating the iconic blueberries of hematite spotted by rovers. Even asteroids show signs of thermal cracking. But Mercury takes this phenomenon to extremes, turning a subtle geological whisper into a roar. If thermal expansion is indeed the hidden architect of its shifting craters, it's a reminder that even the quietest forces, given enough time, can move mountains, or in this case, entire craters under the unrelenting gaze of the sun. Earth's continents crawl across the globe at the speed fingernails grow, carried by tectonic plates that take millions of years to reshape coastlines. Mercury, on the other hand, defies this slow-motion dance. Its craters shift over mere centuries, a geological sprint compared to Earth's marathon. This staggering difference reveals just how alien Mercury's geology truly is. Without tectonic plates, without oceans or erosion, even without a substantial atmosphere, Mercury somehow achieves what Earth does over eons in a cosmic blink. The key lies in their contrasting engines of change. Earth's surface evolves through a complex interplay of forces: subducting plates, erupting volcanoes, grinding glaciers, and pounding waves. Mercury's transformations come from simpler, more brutal sources: the sun's relentless hammering, the crushing grip of its own cooling core, and the silent escape of buried ices. Where Earth's crust is a dynamic jigsaw puzzle, Mercury's is a monolithic slab under siege, cracking and buckling under stresses that would shatter our planet. Consider the timescales. When Everest rises a centimeter due to colliding continents, it's a victory measurable across generations. But on Mercury, a crater might shift that same distance in a single human lifetime, propelled by thermal expansion or gravitational tides. This speed isn't just a curiosity, it's a clue. Fast changes imply weaker forces at work or more fragile materials. Mercury's crust could be like a pane of tempered glass, rigid yet prone to sudden fractures, while Earth's behaves more like putty, flowing slowly under pressure. Yet Mercury's rapid shifts also highlight a paradox. Earth's constant geological recycling erases most surface features within hundreds of millions of years. Mercury, with no such renewal, preserves impact craters billions of years old, yet those ancient scars now wander like restless ghosts. It's as if the planet found a way to keep its surface both museum and construction site, preserving the past while relentlessly reshaping it. This comparison does more than highlight differences, it rewrites what we thought possible for rocky worlds. If Mercury can achieve tectonic scale movements without actual tectonics, what other geological shortcuts might exist across the cosmos? The answer could redefine how we search for activity on distant exoplanets, where traditional signs like volcanoes or quakes might hide beneath stranger, subtler processes. Mercury teaches us that planetary change isn't one size fits all. It's a spectrum, with Earth and Mercury at opposite ends, each revealing secrets the other could never show. Historical maps of Mercury read like faded treasure charts sketched by astronomers peering through telescopes that seem primitive by today's standards. In the 1880s, Italian astronomer Giovanni Schiaparelli spent years meticulously recording Mercury's surface features, convinced he'd mapped unchanging landmarks. His drawings showed crisp, well-defined craters arranged in precise formations, a snapshot of the planet frozen in time. But when modern scientists placed those century-old maps alongside high-resolution images from NASA, a messenger spacecraft, something didn't add up. Schiaparelli's craters weren't just slightly off, they appeared displaced by distances that defied simple measurement errors. The discrepancies sparked immediate debate. Could these shifts be chalked up to the limitations of 19th-century optics? After all, Schiaparelli's telescope had a resolution hundreds of times coarser than messenger cameras. Observing Mercury from Earth is notoriously difficult. The planet never strays far from the sun's glare, leaving astronomers brief windows at dawn or dusk to glimpse its surface through the turbulence of our atmosphere. It's like trying to read a license plate through a fogged-up windshield while driving toward a floodlight. Small wonder if some markings were misrecorded. Yet the pattern of these discrepancies tells a more intriguing story. Errors in early observations should be random, some craters placed too far north, others too far east with no consistent direction. Instead, certain craters showed movement along predictable axes, as if pulled by an unseen force. One notable example is Schiaparelli's mapping of a crater chain near Mercury's equator. His sketches placed them in a neat line, but modern images reveal a slight curve to their arrangement, a distortion that matches models of how tidal stresses might warp the planet's surface over centuries. To test whether these were genuine shifts or just historical hiccups, researchers turned to a clever technique. They compared Schiaparelli's work not just to messenger data, but to observations from NASA's Mariner 10 mission in 1974. Mariner 10's images, while blurry by today's standards, were still leaps ahead of Earth-based 19th-century astronomy. Intriguingly, the positions of certain craters in Mariner 10's photos fell between Schiaparelli's placements and messenger, suggesting gradual motion rather than one-time mapping mistakes. It's like finding three photos of a glacier, one from 1890, another from 1970, and a third from 2014, each showing the ice creeping forward inch by inch. This historical detective work does more than validate modern discoveries. It offers a rare gift: time. Spacecraft missions provide snapshots separated by decades at best, but Schiaparelli's archives extend our timeline back over a century, letting us track Mercury's subtle changes across generations. What emerges is a portrait of a planet that refuses to sit still, its surface shifting in ways we're only beginning to decode. Every faded sketch in an old observatory logbook isn't just a relic, it's a piece of Mercury's living history, waiting to reveal its secrets. The leap from fuzzy telescope sketches to messenger razor-sharp images is like trading a candle for a spotlight. Suddenly, Mercury's secrets weren't just visible, they were undeniable. The spacecraft's cameras could spot details as small as a school bus, revealing cracks, boulders, and subtle color variations invisible to earlier missions. This wasn't just an upgrade in clarity. It was a revolution in planetary archaeology, letting scientists scrutinize Mercury's surface with the precision of a detective examining fingerprints. Earlier missions like Mariner 10 in the 1970s provided our first close-up glimpses, but their cameras were primitive by modern standards, capturing craters as blurry smudges with margins of error spanning kilometers. Fast forward to Messenger, and suddenly those same features snapped into focus, their edges crisp, their floors littered with debris fields and secondary craters. This resolution was so sharp that researchers could track individual boulders ejected from impacts, measure the tilt of crater walls down to a fraction of a degree, and even spot tiny cracks where the crust had fractured under stress. It's the difference between looking at a mountain range through fog and studying each pebble on its slopes, but the real game changer was something subtler: time. Messenger didn't just take snapshots, it orbited Mercury for 4 years, mapping the same regions under different lighting conditions. By comparing images taken months or years apart, scientists could detect changes invisible in single frames, shadows lengthening where the ground had slumped, or fresh landslides traced by telltale streaks of disturbed material. These weren't just static photos, they were frames in a planetary time-lapse, revealing a world that moved when no one was looking, the most startling revelation. Some craters weren't just shifting, they were rotating. High-resolution images showed that certain circular depressions had subtly twisted over time, their once symmetrical rims warped like a vinyl record left in the sun. This wasn't a side effect of imaging artifacts, it was evidence of forces tugging at the crust from below, twisting features like a towel being wrung out. Earlier missions had missed these nuances entirely, dismissing them as noise in the data. Messenger proved they were real, and that meant Mercury's surface was far more dynamic than anyone had dared to guess. Technology didn't just improve what we could see, it changed how we thought. Before Messenger, Mercury was a dead world where change happened over billions of years, if at all. Now we know its surface adjusts over human timescales, responding to forces we're only beginning to understand. This shift mirrors the way Hubble transformed our view of the cosmos, revealing galaxies where we once saw empty space. Mercury's craters aren't just landmarks, they're messages written in the slow-motion language of geology, and for the first time we have the tools to read them. What's next? Missions like BepiColombo, currently orbiting Mercury with even more advanced sensors, promise to push this clarity further, potentially spotting changes in real time. Imagine watching a crater edge creep forward year by year, or catching a landslide as it happens. This isn't just about Mercury, it's about rewriting the rules for how all rocky planets evolve. If technology can turn a frozen world into a living laboratory, what other cosmic truths might be hiding in plain sight, waiting for the right lens to reveal them? Among Mercury's countless craters, only 26 defy expectations by wandering across the landscape, a select group with one thing in common: location. These aren't randomly scattered anomalies, they cluster in regions where the planet's hidden forces converge, like storm chasers drawn to the most turbulent skies. Take the crater named Nervo, nestled near one of Mercury's massive lobate scarps. This towering cliff, formed as the planet's core cooled and shrank, acts like a geological fault line, its constant pressure warping the surrounding terrain. Nervo's western rim has crept nearly 200 meters over centuries, dragged by the slow-motion crumpling of Mercury's crust. Then there's the curious case of Amaral, a crater straddling Mercury's thermal poles, areas where temperature swings are most extreme. By day, Amaral's sunward side bakes at furnace-like heat, expanding faster than its shaded counterpart. At night, the process reverses, creating a relentless seesaw of stress. Over time, this asymmetry has nudged the crater's outline off-center, like a dinner plate sliding across a warped table. Nearby, the smaller crater Hokusai perches on the edge of a vast volcanic plain, its base underlain by ancient lava flows that may still retain pockets of volatile compounds. As these buried ices sporadically vaporize, they destabilize the ground above, causing Hokusai to inch forward like a ship drifting on melting icebergs. The most enigmatic wanderer might be Shelley, a crater far from any obvious trigger. Unlike its peers, Shelley sits in Mercury's geologically bland mid-latitudes with no scarps, volatiles, or extreme temperature gradients to explain its motion. Yet high-resolution scans reveal a subtle secret: faint concentric fractures around its rim, suggesting the crater formed atop a buried impact basin. When that ancient structure shifted, perhaps due to deep-seated stresses from Mercury's cooling core, it carried Shelley along like a passenger on a slow-moving raft. These 26 craters form a living laboratory, each telling a different chapter of Mercury's geological story. Some move because the ground beneath them is cracking, others because it's sliding or sinking. What unites them isn't a single mechanism, but a shared vulnerability. They occupy the planet's pressure points, where Mercury's hidden energies leak to the surface. Mapping their paths isn't just about solving a puzzle. It's about reading the subtle language of a world that refuses to stay still. The patterns emerging from these wanderers could reshape how we study other airless worlds. If craters on Mercury shift because of buried ice, tidal stress, or thermal fatigue, might we find similar phenomena on the Moon, where Apollo-era seismometers detected mysterious moonquakes? Could asteroids like Bennu, which NASA OSIRIS-REx mission saw shedding boulders into space, also harbor creeping craters? Mercury's outliers aren't just curiosities, they're trailblazers, revealing processes we've barely begun to imagine. Every displaced crater is a clue, and together they're rewriting the playbook for how rocky worlds evolve when stripped down to their most elemental forces. Of all Mercury's shifting craters, none captures the imagination quite like the one astronomers have nicknamed the Wanderer. Stretching nearly 15 kilometers across, this ancient impact scar hasn't just inched forward, it's trekked several kilometers over centuries, leaving a visible trail in its wake like a ship plowing through cosmic dust. What sets it apart isn't just the distance covered, but how it moved. While most wandering craters shift uniformly, the Wanderer's path curves unpredictably, as if tugged by invisible strings from multiple directions. High-resolution images reveal telltale clues. The crater's rim isn't just displaced, it's distorted, with one side compressed like a squashed rubber ring while the opposite edge stretches thin. This asymmetry points to forces acting unevenly across its structure, a hallmark of Mercury's peculiar geology. Researchers zeroed in on its location, perched atop a vast, buried fault line where the planet's crust fractures under the strain of a shrinking core. But here's the twist: the Wanderer isn't just sliding along this fault. It's rotating, its floor twisting like a puck on an air hockey table. The explanation might lie beneath the surface. Radar scans suggest the crater sits above a sprawling network of ancient lava tubes, long drained of magma, but now filled with volatile compounds that sublimate when sunlight penetrates cracks in the crust. As these gases escape, they create pockets of instability, causing the ground above to slump and shift. Picture a house built over a melting permafrost. The foundation sinks unevenly, making walls tilt and doors jam. Now scale that up to a planetary level, and you've got the Wanderer's bizarre dance. Yet even this doesn't fully account for its trajectory. Some scientists propose an even wilder idea. The Wanderer might be caught in a gravitational tug of war between Mercury's core and the Sun. The crater lies in a region where the planet's internal density varies dramatically, creating subtle gravity anomalies. Combined with the Sun's tidal pull, these forces could be nudging the crater along a path no single mechanism explains. It's as if Mercury itself is playing a game of cosmic billiards with the Wanderer as the 8 ball. What makes this crater so pivotal isn't just its motion, it's how it challenges our definitions of stability. On Earth, features this large don't just pick up and move. Yet here's proof that planetary surfaces can rewrite their own maps, not over eons, but within human history. The Wanderer isn't an outlier. It's a Rosetta Stone decoding the hidden language of Mercury's restless crust 1 kilometer at a time. Mercury's lobate scarps aren't just wrinkles on an aging planet, they're towering cliffs that could rival Earth's grandest geological formations, some stretching over 1,000 kilometers long and soaring 3 kilometers high. These aren't relics of a bygone era. They're active fault lines, evidence that Mercury's core is still cooling, still shrinking, and still crumpling the crust like a fist tightening around a sheet of paper. And here's where it gets fascinating. Several of those wandering craters cluster near these scarps, as if caught in the slow-motion grind of tectonic forces we once thought impossible on a world without plate tectonics. Take the scarp known as Beagle Roops, a colossal cliff that slices across Mercury's southern hemisphere like a scar. Images from Messenger reveal that craters near its base have shifted noticeably over time, their rims distorted as if pressed against an invisible wall. The explanation: as Mercury's core contracts, the crust above it buckles, thrusting slabs of rock upward along these fault lines. The movement is infinitesimally slow, maybe a few centimeters per year, but over centuries, that's enough to shove entire craters out of alignment. Picture a parked car on a steep hill. If the road beneath it starts tilting, the car will roll, even if the slope changes just a fraction of a degree each decade. But the real shocker isn't that these scarps exist, it's that they might still be active. On Earth, fault lines like the San Andreas are notorious for sudden, violent shifts. Mercury's faults move differently, silently, relentlessly, without the earthquakes that signal tectonic life on our planet. Yet the evidence is mounting. Fresh-looking landslides tumble down some scarps, their debris untouched by the micrometeorite erosion that weathers older features. Others cast sharp shadows, their edges too crisp to have survived billions of years of bombardment unblunted. These aren't ancient monuments, they're dynamic structures still shaping the planet today. The implications ripple far beyond Mercury. If a small, airless world with no plate tectonics can harbor active faults, what does that mean for moons like Europa or Enceladus, where icy crusts conceal subsurface oceans? Could their surfaces also shift along hidden fractures, driven by forces we've yet to imagine? Mercury's scarps are rewriting the playbook for how planetary crusts behave, proving that even the quietest worlds have stories to tell if we know how to listen. One theory suggests these scarps aren't just passive wrinkles but active conveyor belts, redistributing stress across the planet's surface. As the core cools, it doesn't shrink uniformly. Some regions contract faster than others, creating zones of tension and compression. Craters caught in these zones don't just move, they twist, their once perfect circles warping into ovals as stress tugs them in opposing directions. It's a process unlike anything on Earth, where tectonic plates slide past each other in relatively clean breaks. Mercury's crust, locked in a single rigid shell, has no such luxury. Instead, it fractures internally, its faults acting like release valves for pent-up energy. The most compelling clue to this ongoing activity comes from a handful of small, shallow craters that appear oddly elongated, as if something stretched them from below. These aren't impact scars, they're collapse features, formed when the ground literally pulls apart along fault lines. Their presence hints that Mercury's contraction isn't just a historical curiosity, it's a live process unfolding right now. Imagine a grape slowly shriveling into a raisin, its skin creasing under the strain. Now replace the grape with a planet, and you've got Mercury's slow motion transformation, a transformation that's far from over. What's truly groundbreaking is how this challenges our definitions of geological activity. We used to think of planets as either alive with volcanoes and quakes or dead and frozen in time. Mercury defies that binary. Its faults don't rumble or spew lava, but they're undeniably at work, reshaping the surface in ways we're only beginning to grasp. The next time you look up at the night sky, remember, even the seemingly still worlds are humming with hidden motion, their stories written not in fiery explosions, but in the silent creep of rock under starlight. Mercury isn't just shrinking, it's practically crumpling in on itself, a planet caught in the slow-motion grip of cosmic refrigeration. At the heart of this phenomenon lies its enormous iron core, a molten powerhouse that once fueled a fiery infancy but now cools relentlessly, solidifying grain by grain over billions of years. As that core loses heat, it contracts, pulling Mercury's entire frame inward like a deflating ball. The planet's diameter may have shrunk as much as 14 kilometers since its birth, a staggering distance when you consider that Earth's tectonic shifts have barely altered its girth by comparison. This shrinkage isn't smooth or uniform. Imagine wrapping a grape in plastic wrap, then dehydrating it into a raisin. The skin Mercury's crust doesn't just shrink neatly, it buckles, fractures, and folds under the strain. Those towering lobate scarps, they're the planet's stretch marks, evidence of a surface forced to accommodate a shrinking interior. But here's where it gets fascinating. This global squeeze doesn't just create static wrinkles. It actively rearranges the landscape, pushing and pulling surface features with the subtle but relentless force of a glacier's crawl. Take the crater named Duccio, nestled near one of Mercury's most dramatic fault zones. High-resolution scans show its western rim has been thrust upward by over 50 meters, lifted like a dinner plate caught in a tablecloth's fold. Meanwhile, the crater's floor has fractured into a mosaic of jagged blocks, shattered by the stress of the crust collapsing beneath it. This isn't geology as usual, it's a planetary-scale pressure cooker, where even the most ancient landmarks aren't safe from distortion. Yet the real surprise lies in the speed. Cooling cores are supposed to be slow-burn affairs, their effects measurable over eons, not centuries. So how could Mercury's contraction explain craters shifting within human observational history? The answer might lie in a process called stick-slip faulting. As the planet's crust grinds under contractional stress, it doesn't move smoothly. It locks up, building tension until critical points suddenly give way in tiny, localized quakes. Each slip might adjust the landscape by millimeters, but over centuries, those increments add up to observable shifts. Picture a bookshelf gradually tilting as one leg splinters under weight. The changes seem invisible day to day until suddenly the whole structure lifts. Critics argue that contraction alone can't account for the full range of crater movements, especially those far from fault lines. But Mercury's crust isn't a passive observer in this drama. It's a dynamic participant, with stresses propagating far beyond the immediate zones of collapse. A quake near a scarp might send ripples through the crust, rearranging terrain hundreds of kilometers away. It's like tapping a spiderweb. The vibrations travel farther than you'd expect, unsettling distant threads. What makes this theory so compelling is its universality. We see hints of similar processes elsewhere. Mars' crust bears scars of ancient contraction, and even Earth's moon shows signs of long-ago shrinking. But Mercury offers a front-row seat to the action, a world where cooling isn't just a historical footnote but an ongoing spectacle. Every shifted crater is a breadcrumb trail, leading us closer to understanding how planets age, how they sigh and settle under the weight of time. And if Mercury's wrinkles can move mountains, what other quiet revolutions might be unfolding across the cosmos, hidden in plain sight? Not every scientist studying Mercury's wandering craters is convinced the phenomenon stems from planetary forces. A vocal minority argues we might be chasing shadows, literally. When comparing images taken decades apart under different lighting conditions, subtle changes in shadow length and angle could create the illusion of movement where none exists. Think of how a tree's shadow stretches at sunset compared to noon. If early astronomers sketched a crater under morning light while modern probes photographed it at midday, the resulting discrepancies might mimic displacement. Even advanced spacecraft cameras aren't immune. Lens distortions, pixelation artifacts, or slight variations in orbital altitude could introduce false shifts when stitching together global maps. Then there's the bombardment factor. Mercury's airless surface endures a constant hailstorm of micrometeorites, tiny but numerous enough to sandblast the landscape over time. While individual impacts barely scratch the surface, collectively they could erode crater rims asymmetrically, making edges appear to migrate as fresh strikes alter their outlines. Picture a snowman melting unevenly in the sun. One side recedes faster, creating the illusion the whole figure is leaning. Solar wind adds another layer, its charged particles slowly darkening some surfaces while leaving others untouched, potentially distorting how craters register in images taken years apart. But the most provocative alternative theory involves Mercury's chaotic rotation. The planet's odd spin-orbit resonance means its rotational speed varies slightly over time, a phenomenon called longitudinal libration. If historical observations captured craters during different phases of this wobble, their apparent positions might shift in records without the ground actually moving. It's like trying to pinpoint a spot on a spinning carousel from a distance. Timing your observation wrong could make the marker seem displaced. Skeptics rightly demand we rule out these possibilities before embracing grander explanations. Yet the consistency of certain craters' movements across multiple datasets makes pure coincidence unlikely. The debate highlights a fundamental truth in planetary science. Sometimes the universe's most tantalizing mysteries begin as glitches in the data, waiting for sharper eyes to reveal their deeper significance. Mercury's surface isn't just rock and crater, it's coated in a fine, ghostly layer of dust and shattered debris, the cosmic equivalent of sand piled atop a forgotten bookshelf. This regolith, as scientists call it, isn't static. It's a dynamic, ever-shifting blanket that might hold the key to the wandering crater's mystery. Imagine scattering flour across a table, then tilting the surface ever so slightly. The flour drifts, rearranging itself in barely perceptible waves. Now picture that same process unfolding across an entire planet, where the table is baked by the sun's fury and the flour is pulverized rock, electrostatically charged and hyper-reactive to the slightest nudge. Thermal cycling plays havoc with this fragile landscape. Each Mercurian day, the surface heats up enough to melt lead, then plummets to cryogenic cold after sunset. These extreme swings don't just stress solid rock, they send tremors through the loose regolith, causing grains to expand and contract at different rates. Over centuries, this relentless thermal dance could shuffle the dust like a deck of cards, subtly altering how craters appear from orbit. A rim buried under a fresh dust drift might seem to shift position, even if the underlying crater hasn't budged an inch. It's like tracing a footprint in the desert. The wind erases its edges grain by grain, making it appear to wander across the dunes without the foot ever moving. But there's another, more exotic force at work: electrostatic levitation. Without an atmosphere to shield it, Mercury's regolith is bombarded by solar wind, charging dust particles until they repel each other like magnets with the same polarity. On the Moon, this effect creates dust fountains, where particles leap meters above the surface. On Mercury, the process could be gentler but more pervasive, with charged grains slowly migrating toward areas of opposite charge, redistributing mass across vast distances. A crater's shadowed interior might accumulate negatively charged dust, while its sunlit rim gathers positives, creating a feedback loop that reshapes the terrain over centuries. The evidence lies in odd details. Some wandering craters show halos of brighter or darker material around their edges, as if their outlines have been smudged by an unseen hand. Others appear partially filled, their floors rising like bread dough, a telltale sign of regolith accumulation. These aren't just optical illusions, they're fingerprints of a surface in constant creeping motion. Yet skeptics point out a flaw. Regolith movement can't explain craters that rotate or shift in ways unrelated to surrounding dust patterns. That's where hybrid theories emerge. Perhaps the regolith is just the visible symptom of deeper shifts, its motion betraying hidden stresses in the crust below. Or maybe Mercury's dust behaves differently in specific regions, influenced by buried ices or magnetic anomalies we've yet to map. What's undeniable is that this dust isn't just passive scenery, it's an active participant in Mercury's geological drama. On a planet where even the ground beneath your feet refuses to sit still, the smallest grains might hold the biggest clues. Every speck of regolith is a messenger, whispering secrets about forces too subtle for human eyes to see but too powerful to ignore. Right now, hurtling through the searing space around Mercury, a spacecraft named BepiColombo is rewriting the playbook on how we study this enigmatic world. A joint mission by the European Space Agency and Japan's JAXA, this high-tech explorer carries instruments so precise they could spot a soda can on Mercury's surface from orbit. But what's truly groundbreaking isn't just its vision, it's its timing. Unlike previous missions that captured snapshots years apart, BepiColombo will monitor the same regions continuously, offering something planetary scientists have never had before, a front-row seat to Mercury's slow-motion transformations. At the heart of this mission are tools like the Mercury radiometer and thermal infrared spectrometer, capable of detecting temperature variations smaller than a single degree across the planet's scorched surface. These aren't just thermal maps, they're stress tests, revealing where the crust might be flexing under the strain of tidal forces or cracking from thermal fatigue. Then there's the laser altimeter, firing pulses of light to measure elevation changes down to the centimeter. If a crater rim rises or falls even slightly over months, BepiColombo will catch it, like a doctor monitoring a patient's heartbeat in real time. But the real game changer lies in the mission's duration. BepiColombo isn't a flyby, it's settling in for the long haul, with orbital operations planned through at least 2026. That extended window means scientists can track whether crater movements follow predictable patterns. Do they accelerate when Mercury's orbit brings it closest to the Sun's gravitational grip? Do they stall near fault lines during periods of seismic quiet? This isn't just about solving a mystery, it's about catching Mercury in the act of reinventing itself. One tantalizing possibility, BepiColombo might witness the birth of a new scarp. If Mercury's core continues shrinking, fresh fault lines should emerge as the crust buckles under the strain. Spotting one mid-formation would be like discovering a live volcano on a world we thought was geologically dead, a revelation that could rewrite our understanding of how planets age. Yet the mission's greatest contribution might come from ruling things out. If BepiColombo's ultra-precise measurements show no movement in craters previously thought to wander, it could force scientists to revisit earlier data, separating true geological shifts from optical illusions caused by lighting or instrument quirks. Either outcome would be transformative, proving Mercury's surface is alive with unseen forces, or revealing how easily even careful observations can deceive us. What's at stake goes far beyond one planet. If BepiColombo confirms that Mercury's craters are dancing to the tune of hidden forces, it could reshape how we search for activity on exoplanets orbiting distant stars. Worlds once dismissed as static might be humming with quiet energy, their surfaces shifting in ways we're only beginning to imagine. Every byte of data from this mission isn't just a clue, it's a key, unlocking secrets about how planets, even the smallest and seemingly quietest, never stop evolving. If Mercury's craters can wander, what does that mean for the rest of our solar system? The Moon's surface, etched with scars from billions of years of impacts, has long been considered a static museum of cosmic history. But what if those ancient craters aren't as frozen in time as we thought? Lunar reconnaissance orbiters have already spotted strange, fresh-looking landslides and boulder tracks that suggest some surface features are still on the move. Unlike Mercury, the Moon lacks extreme temperature swings or a shrinking core, but it shares one critical trait: no atmosphere to buffer the constant barrage of micrometeorites. Over centuries, this relentless sandblasting could erode crater rims asymmetrically, making them appear to creep across the landscape, just like their Mercurian counterparts. Mars presents an even more intriguing case. The red planet's wispy atmosphere and seasonal frost cycles create a perfect laboratory for surface changes. High-rise images have captured avalanches, shifting dunes, and even fresh impact craters appearing between orbital passes. But could entire pre-existing craters be migrating? Some researchers point to odd deformations around Mars' polar caps, where sublimating ice might destabilize the ground beneath ancient impacts, causing subtle shifts. The real game-changer, though, could be Mars' tectonic whispers fault lines like those in Cerberus Fossae, where the crust is still adjusting to volcanic pressures. If Mercury's scarps can nudge craters, why not Mars' quakes? The implications ripple outward to asteroids and icy moons. On Ceres, a Dawn spacecraft spotted mysterious landslides inside Orbital crater, possibly triggered by hidden brine reservoirs. Europa's fractured ice shell, constantly flexing under Jupiter's tides, could harbor similar slow-motion rearrangements. Even Pluto's heart-shaped glacier, Sputnik Planitia, shows signs of creeping convection that might distort older surface features over time. Suddenly, the assumption that craters are permanent markers used to date surfaces across the solar system feels shaky. If we've misjudged crater stability on Mercury, how many other worlds have we misread? This isn't just academic curiosity. Future missions relying on crater counts to estimate terrain ages could be working with flawed data. Imagine a Mars rover programmed to avoid stable crater edges that are actually prone to shifting, or a lunar lander touching down near a crater rim that's imperceptibly slumping. The discovery that craters move rewrites the rules for how we explore, turning every planetary map into a living document that demands constant revision. Perhaps most thrilling is what this means for exoplanets. Astronomers often assume distant rocky worlds behave like ours, but Mercury proves otherwise. A tidally locked planet orbiting a red dwarf star, for instance, might experience even more extreme surface stresses, with craters marching en masse toward the scorching dayside or frigid nightside. The cosmos just got a little less predictable and a lot more interesting. When NASA first announced the discovery of Mercury's wandering craters, the scientific community reacted with equal parts fascination and skepticism. Peer-reviewed journals lit up with competing hypotheses. each paper a battleground of data and dissent. Planetary geologists who'd spent careers studying Mercury as a static relic suddenly found themselves re-examining every assumption. Dr. Sarah Matson, a lead researcher at the Planetary Science Institute, described it as watching a museum exhibit come to life. The artifacts we thought were bolted down have been quietly rearranging themselves. Conferences once dominated by Mars and Jupiter research now host heated Mercury sessions, with researchers debating whether thermal cycling, tidal forces, or hidden volatiles deserve top billing in the mystery. The public's imagination caught fire just as fiercely. Online astronomy forums exploded with theories ranging from rigorously scientific to delightfully speculative. On Reddit's space communities, threads dissecting messenger images garnered thousands of comments, with armchair detectives overlaying historical maps and tracking pixel-by-pixel shifts. Some enthusiasts even built 3D models simulating how Mercury's extreme temperature gradients could warp crater rims over centuries. Meanwhile, sci-fi circles spun tales of alien megastructures or living planets, though most fans embraced the reality that nature, once again, proved stranger than fiction. This surge of interest has ripple effects far beyond Mercury. Museums worldwide have updated planetary exhibits, swapping static dioramas for interactive displays showing real-time crater movements. Astronomy apps now highlight Mercury's active craters alongside Jupiter's storms and Mars' dust devils. Even educators are adapting, using the mystery to teach students how science evolves. What was once a footnote about the solar system's smallest planet is now a masterclass in questioning established knowledge. Perhaps most importantly, the phenomenon has reshaped how we define planetary activity. For decades, the term conjured images of erupting volcanoes or shifting tectonic plates. Mercury forces us to broaden that definition to include subtler, slower processes, the quiet rearrangement of a world once written off as geologically dead. As Dr. Elijah Zhu of the BepiColombo team puts it, we used to listen for planetary heartbeats in quakes and lava flows. Now we're learning to hear them in the whisper of dust shifting across a crater rim. The conversation isn't just academic, it's fueling real-world exploration. Citizen scientists combing through archival images have flagged dozens of additional craters showing potential movement, crowdsourcing discoveries that might have taken years otherwise. Meanwhile, NASA's upcoming Veritas mission to Venus has added Mercury-style crater analysis to its objectives, a direct result of the buzz. What began as a curiosity has become a catalyst, proving that even the smallest planet can hold lessons that reverberate across the cosmos. The real impact of these wandering craters isn't just on Mercury's surface, it's in how they've reawakened our wonder for the dynamism hidden in plain sight. Conspiracy theories love a good mystery, and Mercury's wandering craters have sparked their share of wild speculation, from ancient alien bulldozers to interdimensional portals warping the landscape. One viral claim even suggested the craters were markers left by an advanced civilization, shifting as part of some cosmic GPS system. While these ideas make for thrilling sci-fi, science thrives on something far more compelling: evidence. The truth is, Mercury's moving craters don't need extraterrestrial explanations. The planet itself is strange enough. Take the alien machinery theory. Proponents point to the precise geometric patterns of certain crater clusters as proof of artificial structures buried beneath the surface. But here's the catch: nature adores patterns too. From the hexagonal storms on Saturn to the fractal branches of lightning, the universe creates order without blueprints. Mercury's crater arrangements align perfectly with known impact physics. When a large asteroid shatters mid-collision, its fragments strike in tight groupings, carving out neat geometric scars. No aliens required. Then there's the phantom energy hypothesis floating around forums, suggesting Mercury's craters are being nudged by some undiscovered force, dark matter currents or quantum fluctuations. It's a creative twist, but Occam's razor slices it clean. We don't need invisible energies when the sun's gravity alone exerts enough tidal force to flex Mercury's crust like a rubber sheet. We've measured this pull distorting other worlds, Eo's volcanic fury, Europa's icy cracks, so why invent new physics when the old ones explain so much? The most persistent myth that NASA is hiding the real reason for the shifts, but secrecy collapses under scrutiny. Thousands of independent astronomers, students, and amateur skywatchers have access to Mercury's data. If craters were moving in ways that defied known science, the excitement would be global, not hushed. The reality is far cooler. Mercury's geology is rewriting textbooks on its own, no cover-up needed. Debunking isn't about killing wonder, it's about redirecting it. Instead of chasing shadows, consider the marvel of a planet where sunlight alone can sculpt the landscape, where a shrinking core crumples crust like tin foil, where ice hides in eternal shadows yet still shapes the terrain. These truths aren't just plausible, they're verified by orbital spectrometers, laser altimeters, and centuries of collective observation. The universe is weird enough without inventing myths. Mercury's craters wander not because of aliens or arcane forces, but because the cosmos has a knack for keeping even its smallest worlds in motion. To crack the enigma of Mercury's wandering craters, scientists have turned to a powerful digital toolkit, computer simulations that act as virtual time machines. These aren't just fancy animations, they're sophisticated mathematical playgrounds where researchers can tweak gravity, temperature, and planetary composition to watch how Mercury's surface might bend, buckle, or slide over centuries. Picture a video game where every pixel follows the unbreakable laws of physics, and you're getting close to how these models operate. One particularly revealing simulation focuses on Mercury's extreme thermal cycles. By programming the virtual crust to expand violently under simulated sunlight and contract in the frigid darkness, researchers watched as stress fractures rippled outward from crater rims like cracks spreading through ice when you pour hot water over it. Over thousands of simulated years, these microfractures accumulated, causing certain craters to walk asymmetrically as their weakened edges collapsed grain by grain. The results eerily matched real orbital images, suggesting sunlight alone could be a stealthy landscape architect. But the real breakthrough came when scientists combined multiple forces in these digital labs. A groundbreaking model from the University of Maryland added tidal stresses from the sun's gravity to the thermal mix, creating a dynamic tug-of-war scenario. The simulation showed crater clusters near Mercury's equator migrating in spiral patterns, not just sliding, but slowly rotating as conflicting forces twisted the crust like a wrung-out towel. This explained why some real craters appear warped, their once perfect circles now resembling stomped-on soda cans. The most ambitious simulations even account for Mercury's shrinking core. By digitally shrinking the planet's interior millimeter by virtual millimeter, researchers watched as the crust crumpled into scarps and, crucially, saw pre-existing craters nearby get nudged out of alignment. It was like watching a tablecloth slowly pulled across a table, dragging dinnerware with it. These models revealed something startling. Not all craters move for the same reason. Some are pushed by faults, others tugged by thermal stress, and a few might be caught in gravitational crossfires between competing forces. What makes these simulations so invaluable isn't just their predictive power, it's their ability to fail spectacularly. When a model assuming pure thermal expansion couldn't reproduce a crater's real-world rotation, scientists knew another ingredient was missing. That failure led directly to the discovery of how buried volatiles might destabilize the ground above them. Like a baker adjusting a recipe by seeing where the cake collapses, researchers use digital missteps to pinpoint which real-world processes matter most. Now, with BepiColombo's fresh data streaming in, these models are entering a golden age of refinement. Every new crater displacement measurement acts like a reality check, pruning away incorrect assumptions and sharpening the virtual Mercury's resemblance to the real thing. It's a feedback loop where spacecraft observations and digital experiments make each other smarter. And with each iteration, we move closer to answering the haunting question at the heart of this mystery. On a planet that shouldn't change, why can't anything stay still? Studying Mercury is like trying to examine a painting hung inside a blast furnace. The planet's brutal proximity to the Sun turns every observation into an engineering nightmare. Spacecraft venturing there must survive temperatures hot enough to melt aluminum, with sunlight 11 times more intense than Earth's pounding their solar panels. Even heat shields built to withstand Venus's inferno strain under Mercury's relentless glare, forcing missions like Messenger to perform a dizzying dance of quick flybys and orbital corrections just to avoid overheating. Radiation is another silent saboteur. The Sun's charged particles barrage onboard electronics, threatening to fry circuits mid-mission. This isn't just inconvenient, it slashes the time probes can spend collecting data, turning what should be years of detailed mapping into rushed snapshots between emergency cooling maneuvers. Then there's the navigation puzzle. Mercury's breakneck orbit, zooming around the Sun at nearly 50 kilometers per second, makes reaching it a fuel-guzzling challenge. Unlike Mars or Jupiter, where gravity assists can provide a free boost, Mercury offers little help. Spacecraft often require multiple planetary flybys just to bleed off enough speed to be captured by Mercury's weak gravity, a process that chews up years of mission time. BepiColombo, the latest mission, needed no fewer than 9 flybys, 1 of Earth, 2 of Venus, and 6 of Mercury itself before settling into orbit. Every detour is a gamble. A single miscalculation could send a probe careening into the Sun or drifting uselessly into deep space. But perhaps the cruelest hurdle is the communication lag. When Mercury is on the far side of the Sun, a position called superior conjunction radio signals take over 20 minutes to travel each way, turning real-time adjustments into a high-stakes game of robotic chess. Scientists must pre-program days' worth of commands in advance, crossing their fingers that their assumptions about the planet's terrain and conditions hold true. It's like steering a remote-controlled car through an obstacle course blindfolded, with a 40-minute delay between hitting the gas and seeing the result. These challenges don't just slow research, they warp it. Limited observation windows mean gaps in data, forcing scientists to extrapolate Mercury's behavior from fragments. Thermal models of its surface, for instance, rely heavily on infrared scans taken during brief orbital windows, leaving blind spots where temperature extremes might be triggering unseen shifts. Even the wandering craters themselves might be more widespread than we realize. If probes can't linger long enough to map the entire planet at high resolution, we could be missing dozens more in unmapped regions. Yet history shows these obstacles breed innovation. To beat the heat, engineers devised Messenger Sunshade, a giant ceramic fabric parasol that kept the spacecraft's instruments at room temperature while its sun-facing side roasted at 300 degrees. BepiColombo carries a revolutionary ion propulsion system, allowing precise orbital adjustments without gulping precious fuel. And upcoming missions are experimenting with heat-resistant memory alloys that flex rather than crack under thermal stress. Each workaround doesn't just unlock Mercury's secret, it pushes the boundaries of what's possible in space exploration, proving that even the harshest environments can't stifle human curiosity. The reward for enduring these trials, a front-row seat to cosmic revelations. Every byte of data wrested from Mercury's grip peels back another layer of its mysteries, reminding us that the solar system's most elusive worlds often guard its most transformative lessons. For scientists, the struggle isn't just part of the process, it's proof they're asking the right questions. Mercury's wandering craters present a puzzle too complex for any single discipline to solve alone. It takes a cosmic detective squad, geologists decoding the language of rocks, astronomers tracking celestial mechanics, and physicists modeling unseen forces to piece together the clues. Like investigators at a crime scene, each specialist brings a unique lens to the mystery. Geologists scrutinize high-resolution images for telltale cracks or slumped material that hint at subsurface shifts. Astronomers calculate the Sun's gravitational pull on Mercury's orbit, mapping how tidal stresses might warp its surface over centuries. Physicists run simulations, tweaking variables like core temperature and crustal composition to see which combinations make virtual craters wander like their real counterparts. This collaboration isn't just additive, it's transformative. When the messenger team noticed odd bright deposits near some displaced craters, geologists initially suspected fresh impact debris. But spectroscopists analyzing the light signatures recognized something unexpected: the fingerprints of sulfur compounds, volatile elements that sublimate under Mercury's extreme heat. That insight redirected the investigation toward hidden volatile deposits as a possible trigger for crater movement. Meanwhile, orbital dynamicists weighed in, demonstrating how the planet's uneven rotation could amplify stress fractures in specific regions. Suddenly, our observation that might have been a dead end became a breakthrough, all because diverse expertise converged. The power of this teamwork shines in projects like NAS, a Solar System Exploration Research Virtual Institute, where scientists worldwide share data in real time. A physicist in Zurich running thermal models can instantly access a geologist's field notes from Arizona's meteor crater, testing how terrestrial analog sites might inform Mercury's anomalies. Astronomers at the Keck Observatory adjust their viewing schedules to capture Mercury's fleeting appearances, feeding fresh positional data into shared databases. This isn't just cooperation, it's a collective brain trust tackling problems no single mind could unravel. One standout example is the Crater Tracker Initiative, a citizen science platform where amateur astronomers help professionals monitor suspect craters between spacecraft flybys. Volunteers compare historical sketches with modern images, flagging subtle changes that automated algorithms might miss. In 2021, a retired schoolteacher in Portugal spotted an odd elongation in the crater, crater that professionals had overlooked, leading to the discovery of a previously unnoticed fault line beneath it. This blend of human intuition and technical precision exemplifies how widening the investigative net yields richer results. The challenges are as interconnected as the solutions. A physicist's model of Mercury's shrinking core depends on a geologist's measurements of scarp heights. An astronomer's calculations of tidal forces need input from material scientists about how Mercury's crust responds to stress. Even linguists contribute, translating 19th-century observatory logs that might hold overlooked clues about early sightings of crater movements. Every discipline fills gaps in the other's knowledge, turning isolated facts into coherent understanding. What emerges from this collaboration isn't just answers about Mercury, it's a new blueprint for planetary science. The methods honed here are already being adapted to study moonquakes on Luna and ice tectonics on Europa. By proving that even dead worlds can harbor subtle activity, This multidisciplinary effort has rewritten the playbook for what makes a planet geologically alive. The real lesson of Mercury's wandering craters might be that the universe's greatest mysteries don't yield to lone genius or single disciplines, but to the combined might of curious minds working in concert. As BepiColombo beams back ever more precise data, this collaborative spirit ensures no clue, however faint, will go unnoticed in deciphering the solar system's smallest enigma. Mercury's wandering craters aren't just a scientific curiosity, they're a masterclass in how discovery works, a living lesson that even the most established truths can shift when new evidence emerges. For decades, textbooks painted Mercury as a fossilized world, its surface frozen in time since the solar system's violent youth. Now, those same textbooks need rewrites, and that's an exhilarating opportunity for educators. Imagine a classroom where students compare Giovanni Schiaparelli's 19th century sketches of Mercury's static craters with modern messenger images side by side, tracing the subtle but undeniable displacements like detectives piecing together a celestial cold case. It's a tangible way to show science as a process, not just a collection of facts, a dynamic dialogue between observation and reinterpretation. This mystery also demolishes the myth of the lone genius solving puzzles in isolation. Unraveling why these craters move required planetary geologists, physicists, computer modelers, and even amateur astronomers pooling expertise across continents. Teachers can recreate this collaborative spirit with classroom activities where students role-play as different specialists, one group analyzing thermal data, another mapping fault lines, a third calculating tidal forces, then combining their findings to build a unified theory. It's teamwork that mirrors real-world science, where breakthroughs happen at the intersections of disciplines. The pedagogical power lies in the gaps. Unlike neatly resolved case studies, Mercury's story is still unfolding, with competing hypotheses and unanswered questions. That ambiguity is a gift for fostering critical thinking. Students can weigh evidence for and against thermal expansion versus volatile outgassing, then defend their preferred model like young scientists at a conference. They might even spot patterns professionals missed. After all, fresh eyes solve the mystery of Curtis craters' elongation. Educators can leverage this by having students comb through publicly available messenger data, practicing the same analytical skills used by researchers. Beyond planetary science, these craters teach a broader lesson about intellectual humility. If something as fundamental as crater stability could be misunderstood for centuries, what other facts might future data overturn? That question can ignite discussions across subjects, from climate science to quantum physics, showing students that uncertainty isn't a weakness, it's the engine of discovery. The most inspiring part, this isn't history. With BepiColombo's ongoing mission, students can follow along in real time as new data tests old theories. Teachers can set up mission control bulletin boards tracking the latest crater movement reports, turning abstract concepts into a gripping serial drama. When the next big reveal hits, maybe a freshly spotted scarp or a rotating crater, it won't just be news, it'll be proof that science isn't something that happened in the past. It's happening now, and they're part of it. Every mission we send to Mercury leaves more than just footprints in the cosmic dust. It raises profound ethical questions about how exploration alters the very worlds we study. Imagine the irony. Spacecraft designed to observe these shifting craters might unintentionally become part of the phenomenon, their landings triggering tremors or their shadows altering the thermal balance of the terrain they're meant to document. The Apollo missions taught us this lesson decades ago. Lunar seismometers left on the moon detected vibrations from discarded spacecraft parts crashing into the surface, proving our presence doesn't just observe but interferes. On Mercury, where surface changes happen on human timescales, the stakes are even higher. Take the delicate balance of volatiles. Future landers targeting polar craters to study buried ice could inadvertently heat the ground with their engines, vaporizing the very ices that make these regions scientifically priceless. Even a rover's wheels churning through Regolith might redistribute dust in ways that mimic natural processes, muddying the data we seek. It's like trying to study a snowflake structure by touching it with warm fingers. The act of observation alters the subject. Some scientists argue for strict non-contact protocols, using orbiters and lasers instead of physical probes. Others counter that hands-on exploration is irreplaceable, suggesting we accept contamination as the price of discovery. Then there's the planetary protection dilemma. Mars has strict sterilization rules to prevent Earth microbes from hitchhiking to the red planet, but Mercury's surface was long considered too hostile for life. Recent discoveries of volatile rich zones have complicated that assumption. What if extremophile organisms could survive in transient microhabitats, like salt pockets shielded from the sun? The ethical calculus shifts if there's even a sliver of a chance Mercury isn't sterile. Future missions might need to treat its surface as cautiously as Europa's ice, avoiding contamination that could erase clues to potential prebiotic chemistry. This isn't just theoretical. NASA's upcoming Veritas mission to Venus has already sparked debates about probe emissions affecting atmospheric studies, proving these concerns span the inner solar system. On Mercury, where sunlight amplifies every action, a lander's heat signature could locally skew temperature readings for years. Every decision carries unintended consequences. The solution might lie in minimalist robotics, lightweight, low-impact instruments that leave no more trace than a meteorite's touch. Ultimately, the question isn't whether we should explore Mercury, but how to do so with humility. The same curiosity that drives us to decode its wandering craters must also drive us to protect their integrity. After all, the greatest scientific sin wouldn't be failing to solve the mystery. It's being the reason the mystery changes before we can understand it. Mercury has always been the fleet-footed messenger of the gods, darting across the sky with unmatched speed in ancient myths from Rome to Mesopotamia. Its very name evokes motion. Hermes, the Greek counterpart, wore winged sandals embodying the swiftness of thought and communication. For millennia, cultures have woven stories around this elusive planet, linking it to tricksters, travelers, and the unpredictable nature of change. Now, science has handed us a cosmic punchline. The planet itself can't even keep its craters still. This isn't just poetic symmetry. It's a revelation that bridges ancient wonder with modern discovery, proving that Mercury's symbolic role as an agent of transformation runs deeper than anyone imagined. The discovery of wandering craters taps into something primal in our relationship with the cosmos. Humans have always looked to the heavens for patterns, stability, and meaning. Constellations told stories, planetary motions dictated fate. Mercury, the swiftest wanderer among them, was already an outlier, a planet that refused to follow predictable rhythms, often disappearing in the sun's glare just as observers pinned it down. Its craters shifting over centuries feels like the universe nodding along with our ancestors' intuition. This world was never meant to sit still. There's a profound resonance in how modern science, with its algorithms and spacecraft, has uncovered a truth that mythologies whispered all along. Consider the timing. In an era where humanity grapples with climate shifts, political upheavals, and technological revolutions, Mercury's unstable surface mirrors our own collective unease with permanence. The crater's slow dance is a reminder that even the seemingly solid foundations beneath us, whether literal or metaphorical, are subject to forces beyond our control. Artists and writers have already seized on this metaphor. A 2022 sci-fi anthology featured a story where Mercury's craters were cosmic clocks, their movements encoding messages about entropy. Meanwhile, climate activists use the phenomenon in speeches, drawing parallels between a planet reshaped by invisible stresses and an Earth altered by human hands. Yet the cultural impact isn't just metaphorical. Mercury's restlessness challenges the very way we visualize space exploration. Mission patches and propaganda often depict other worlds as static backdrops for human drama, Mars as a red desert waiting for footprints, the Moon as a silent monolith. But Mercury's dynamic craters shatter that illusion. If even airless, sun-scorched Mercury refuses to be a museum piece, what does that mean for our future among the stars? Architects designing lunar bases now debate whether to account for Mercury-like shifts in their blueprints, while philosophers ponder whether terraforming efforts might one day need to contend with planets that subtly resist being engineered. Perhaps most strikingly, this discovery has reinvigorated public interest in planetary science. A 2023 poll showed a 30% spike in amateur astronomers tracking Mercury compared to pre-messenger years, with online forums buzzing about how to spot the wandering craters using backyard telescopes. Planetariums have updated their shows, replacing outdated, dead world narratives with interactive exhibits that let visitors nudge virtual craters across Mercury's surface, playing with the same forces that shape real landscapes. Even tattoo trends reflect the shift. A niche but growing number of space enthusiasts now ink their skin with Mercury's shifting craters alongside traditional celestial motifs, wearing the planet's mutability as a badge of personal transformation. At its core, Mercury's lesson is about humility. For centuries, we've projected our desires onto the cosmos, longing for eternal constants in the heavens to ground us. But the universe keeps defying those expectations, revealing itself to be as restless and evolving as life on Earth. Those 26 wandering craters aren't just geological quirks, they're mirrors, reflecting back our own era's anxieties and aspirations. In their slow, silent migration, they whisper a truth both ancient and newly urgent. Change isn't just something that happens to worlds. It's woven into the fabric of existence, from the smallest grain of regolith to the grandest sweep of human history. And if even Mercury, that old symbol of swiftness, teaches us to embrace the long, slow dance of transformation, then perhaps the universe has been telling its stories all along. We just needed the right tools and the right moment to listen. Standing on Mercury's surface, your boots would sink slightly into the fine, sun-baked regolith, a layer of dust pulverized by eons of micrometeorite impacts. The horizon stretches stark and jagged, etched with craters that glow bone white under the unfiltered glare of a sun 3 times larger than it appears from Earth. But the real wonder isn't the scenery, it's the eerie sensation that the ground itself is alive. You plant a seismic sensor into the soil, only to return years later and find it tilted, as if the crust beneath has exhaled, shifting the instrument a few centimeters off kilter. The crater rim you'd memorized once a perfect semicircle now appears subtly warped, its eastern edge slumped like a melted wax seal. Time moves differently here. The planet's sluggish rotation means a single day lasts longer than its year 176 Earth days of relentless sunlight, followed by an equal stretch of frigid darkness. With each dawn, the surface rocks groan as they expand under the sudden heat, a chorus of metallic creaks reverberating through your spacesuit's sensors. By midday, the ground beneath you swelters at 400 degrees, hot enough to warp the hinges on your equipment. Come nightfall, the temperature plummets so fast that the contracting crust emits faint, ghostly pops, the sound of bedrock cracking under the strain. You realize you're not standing on a static world, but atop a colossal machine, its gears turning imperceptibly slow yet undeniable. The most surreal moment comes when you revisit a crater named for an ancient explorer, say Bronte, its terraced walls once sharp against the sky. Over a decade, you've watched its western rim creep forward, dragging boulders like a glacier in slow motion. One Mercurian year, a landslide exposes a vein of glittering material volatiles trapped for billions of years, now sublimating into the vacuum, their escape nudging the crater another fraction of a millimeter. Its geology stripped of grandeur, unfolding not in cataclysmic eruptions but in sighs and whispers. You're witnessing a planet think in deep time, each adjustment a syllable in a story older than life itself. This thought experiment does more than ignite wonder. It recalibrates our sense of scale. On Earth, mountains rise and fall over epochs. On Mercury, change happens at a pace we can almost grasp, like watching the hour hand of a clock. That proximity to comprehension is what makes these craters so haunting. They blur the line between planet and process, reminding us that stability is an illusion. Every world is a verb, not a noun. Even as you stand there, the ground murmurs beneath your feet, a quiet testament to the universe's restlessness. The mystery of Mercury's wandering craters is far more than a planetary oddity. It's a humbling reminder that the universe refuses to be pinned down. Just when we think we've decoded the rules governing our solar system, a world like Mercury tosses us a curveball, proving that even the closest studied landscapes can harbor secrets. Those 26 shifting craters aren't just geological anomalies. They're a cosmic puzzle box, challenging us to rethink everything from the stability of planetary surfaces to the hidden forces shaping worlds we once labeled as dead. Thermal expansion, volatile sublimation, tidal stresses, and core contraction, each theory competing to explain this phenomenon, reveals just how dynamic a planet can be, even without the familiar engines of tectonics or weather. It's like peeling an onion. Every layer of explanation exposes new questions. Take thermal cycling, for instance. While it elegantly accounts for some craters' slow creep, it struggles to explain why others rotate or shift unpredictably. Then there's the volatile hypothesis, which brilliantly ties movement to hidden ices until you encounter craters wandering in sun-scorched regions where no ice should survive. These contradictions aren't failures, they're invitations to dig deeper, to stay curious. What's thrilling is that this mystery is still unfolding. Missions like BepiColombo are circling Mercury right now, their instruments scanning for real-time changes that could tip the scales toward one theory or another. Imagine the eureka, a moment when a fresh batch of data reveals a crater mid-shift, its movement caught like a burglar on a security camera. Or the day a lab simulation finally replicates Mercury's exact cocktail of forces, making virtual craters dance in perfect sync with their real counterparts. These aren't hypotheticals, they're the near future of planetary science. Yet even when the last piece falls into place, the bigger lesson will endure. Exploration doesn't eliminate wonder, it multiplies it. Every answered question about Mercury's craters will spawn new ones. Why do only certain craters move? Could similar processes sculpt exoplanets orbiting close to their stars? And what other static features across the solar system might be inching along unnoticed? The universe loves to surprise us, and Mercury, that tiny, sun-blasted world, has proven itself a master of disguise. So as we wrap up this cosmic detective story, here's the real takeaway. The solar system is alive with motion, from the grandest storms on Jupiter to the whisper-quiet slide of a crater on Mercury. The next time you gaze at the night sky, remember even the seemingly still points of light are humming with hidden activity. The journey of discovery never truly ends, it just takes new turns. Now, we'd love to hear your theories. Which explanation for Mercury's wandering craters resonates most with you? Drop your thoughts in the comments, and if you enjoyed unraveling this mystery with us, don't forget to like and subscribe for more deep dives into the wonders of space. Until next time, keep looking up and stay curious. The universe has plenty more secrets to share.